I think we have still 10 seconds to go, but we can start. Everybody is excited, I think, to hear Sir Fraser. So welcome everyone. Thank you for coming. It's my great honor and pleasure to introduce Sir Fraser Stoddart, who was so nice to visit us in Brno. Sir Fraser was born in Scotland, in Edinburgh, where he also studied, did his initial studies, and then he also graduated and did his PhD at the University of Edinburgh. Then he traveled quite a bit around the world, and I think he will tell us more in his presentation, until he moved finally to the Northwestern University in the United States, where he is currently the Board of Trustees, Professor of Chemistry, and where he has a group of mechano-stereochemistry, which counts currently about 30 postdocs. He works in supramolecular chemistry and nanotechnology. He is the inventor of a new bond, of mechanical bond, which is very interesting and famous concept, which has been used in preparation of various intriguing compounds, such as catenanes, rotaxanes, or molecular Borromean rings. He has demonstrated that these compounds can be used as molecular shuttles, molecular switches. They can be used as nanoelectronics or nanoelectromechanical systems. Over his career, he published more than 1,300 papers, which are highly cited. And he has guided, led, and inspired a great amount of students. More than 500 PhD and postdoctoral students went through his laboratories, and currently more than 80 of them actually has their own scientific career. He has been awarded by many prizes, out of which probably the most known is the Nobel Prize in Chemistry in 2016, which he shared with Ben Feringa and Jean-Pierre Savage, which was awarded for the design and synthesis of molecular machines. It is my great honor to invite you here. It's gonna be our great honor to listen to your talk. Fraser, the floor is yours.
Thank you. Well, thank you. You've been very generous with your introduction, and you kept it, I think, short enough. Thank you. I want to make a couple of comments before I start, and that is, today has been a lesson in the hosts being prepared out of all recognition compared to any other hosts I've had in the last 2.5 years. So if Esther is here, maybe? No? Anyway, she did an incredible job in getting a group of students informed about my life, that it was to a point where I was wondering, did I actually say that? Did I actually do that? Okay. And then this was taught by the person who interviewed me from the Czech television. I hope I get his name right. Daniel Schrank? Okay. So I've never had a professional interviewer who had delved into so much detail that at one point I was struggling to actually get into what he was referring to. But eventually I got there with a few hints. So the preparation that has been put in for my visit, I would leave you with the comment that has been second to none. And so that makes me feel very warm and very, very much engaged with everybody here. All right, so I'm going to talk about the rise and promise of artificial molecular machines based on the mechanical bond. Now, if we look at machines, engines through the ages, then there is a wheel. This one goes back, I think, about 3,000 years, but I think I'm going to replace it by the one that is in the Old Town Hall here. because it has quite a story to it. So you'll probably in the next lecture, if you ever come to hear me, see the Brno wheel here. But I'm not going to talk much about wheels. I'm going to talk about steam, briefly, electric motors, internal combustion engines, diesel engines, jet engines, rockets, and then look at our own biological machinery, without which we wouldn't, any of us, be sitting here living, and also to end up with the ones close to my heart, namely artificial molecular machines. And I don't for a minute believe that's the end of the story, so there's space for anybody in the room to take it a little bit further. Okay, looking at steam, the image down the bottom here is a fellow Scot, James Watt, his steam engine from 1765. Here's an example from 1883. This is from the United States, from the northern part of Pennsylvania. It was used to pump oil out of the ground. They soon took to wheels, and perhaps the most famous one, at least in the UK, is Stephenson's rocket. You can see this in the Science Museum in London, dating back to 1829. Here is the 1923 variety of the so-called Flying Scotsman that cut the journey down between Edinburgh and London to 6 hours. And here's one from the state of Oregon that is still used to this day to show tourists off the beautiful aspects of that state. If we move to electric engines, then, or motors, here is a device that was, as it were, designed by Faraday, where he was able to convert chemical energy into mechanical energy. Here is one of the first electric motors. So this was a Hungarian, János Sedlik. We'll come back to him later. This is apparently in a museum, probably not all that far from here, and still operates to this day. Here is a 1842 variety, which was a gift from James Joule to Lord Kelvin, the Scottish physicist. And then here are familiar uses of this type of electric motor, or hair dryer, the Tesla car, and here, if you visit China, you become very much aware of this high-speed rail that they're using to connect 60 cities the size of New York.
The Beijing to Shanghai high-speed train has even clocked in speeds up to 480 kilometers an hour. That's about 300 miles an hour.
Quite awesome, to use an American phrase. The internal combustion engine. So here's a patent designed by von Langen, a German, which very quickly made its way into the real combustion engine. I go fast forward to one that's well known, the so-called 4T. This is the one that was brought onto the American market by Ford, and between 1908 and 1927, about 17.5 million of these were sold to ordinary men and women in the US. And then here is what I'm driving today. It's not a Maserati or a Ferrari, it's a Toyota Corolla. The privilege it has is that it has a Northwestern reserve parking place, yeah? And never had Northwestern moved as quickly as they did. This all happened in, I think, less than 48 hours after the announcement of the prize. Diesel engines, well, here's Rudolf Diesel, a German engineer. And when I was putting this talk together, I realized for the first time that diesel was named after someone. Here was one of his early diesel engines, and here is one from 2006, much larger, probably making its way into a cargo ship of some sort. Jet engines, well, that era is normally associated with the Englishman Sir Frank Whittle. And here you see, in modern times, or reasonably modern times, an F-22 taking off, fighter jet, while this Boeing 787 Dreamliner is coming in and landing at Heathrow Airport just over a year ago, having come all the way from Perth in Australia, 9,000 miles in 17 hours, non-stop. Now, here's something that will blow your mind. At any one time now, there are 12,000 of these contraptions in the air. And if we put 200 250 people in each. Then there's 2.5 million people circulating around the Earth. This is a little bit about nearly half the population of Scotland, and probably about a third of the population of the Czech Republic. Is mind-boggling. Yeah? Okay, rocket engines. Well, it wasn't such a pleasant start because the German Air Force used these against Antwerp and Liège and London and so forth. But moving on, after the war, we saw Apollo 11 with Bud Aldrin and Neil Armstrong, as it were, in '69 land on the moon. But I've got a personal connection here. Subsequently, this young lady, Helen Sharman, I was her tutor as an organic tutor at Sheffield University, and I would not have guessed at the time necessarily that she would end up being Britain's first astronaut, courtesy of a Soyuz 2, the Russian mission, in 1991. And so we're often linked up on Twitter, and of course everybody knows that I'm either the Twitter monster or the Twitter master. You can take your and I urge everyone to consider expressing themselves in this medium. Here is a rocket landing, a SpaceX rocket, and that tells you that not only can you lift them off the ground now, but you can safely get them to land. Our biological motors, well, here's one that we have in our muscles, actin, interacting with myosin, and this has been driven by this little rotary motor that's housed in our mitochondria, where you have the influx of ADP, adenosine diphosphate and phosphate, producing ATP, which is really the chemical energy store that is used in these muscles. And if you are a normal adult not involved in any strenuous work during a day, you are generating 40 kilograms of ATP a day. It's amazing, half your body weight. If you are Serena Williams and you're on a tennis court, then the chances are that you will be generating your body weight of ATP each day. We keep the gender balance right, no surprise. Here is a Scotsman that is also winning Wimbledon. It's an interesting dynamic in the UK. When he wins, he's British. When he loses, he's Scottish. Okay, so enough of that. Let's look at going back to molecules. And well, as Andra introduced me, I had a period when I was very much involved in supramolecular chemistry, and that's where you have a receptor and a substrate, to use Jean-Marie Lane's terminology, or CRAMS, host and guest, and they're always flying apart, and you're looking at stability and expressed by stability constants. And this would be the case for this thing here called a pseudoretaxane, which is the precursor to either a retaxane or a catenane. And the point I want to make is once we get here, we're back into a molecular world. And so it was this drive to get back into the molecular world that incentivized me towards the mechanical bond and making mechanically interlocked molecules, where I have to use, and anyone has to use, I think, some supramolecular or molecular recognition interactions, self-assembly, and template-directed synthesis to cross the boundary from complexes to molecules. So catenanes I refer to as mechanically interlocked molecules, or for short, MIMS. And the two examples are the retaxane, and you see this is derived from Latin. And here you see an abacus, so it tells you what sort of things you might be able to do with that molecular species. And here is a 2-catenane, and of course the Olympic sign, which would be a 5-catenane. And the most important thing about this slide, and Wikipedia get it right, they are molecules. Okay, so Mendel roadmap, establishing molecular recognition. We'll look at templating the formation of catenanes and retaxanes. Then we'll look at molecular shuttles and switches, then energy ratchets, radical templation, molecular pumps, and this will take us into the arena of doing chemistry away from equilibrium. And then at the end, there'll be maybe, I doubt it because I have too many slides, but if there is time, we'll look at some philosophy. So establishing molecular recognition. All of this happened quite fortuitously as I had left academia in 1978. I hadn't had a particularly pleasant introduction at the Sheffield University chemistry department, and so I escaped to the corporate laboratory in Runcorn, Cheshire, which is near to Liverpool, of Imperial Chemical Industries. And after a little bit of a story, which I will tell you very briefly, it was wipe out weed killers, which have all these properties, namely diquat and paraquat, that we incorporated into our molecular machinery. Who would ever have guessed that it was weed killers that would be used in their building? So the story really at the corporate lab started with going back to Alfred Werner, Swiss chemist, who was a Nobel laureate back in 1913 for his discovery of the first sphere coordination by organic ligands of transition metals. And he had a disciple in the UK, Joe Chatt, who had spent quite a lot of his early career also at ICI. And so he bequeathed to the company a whole treasure chest of first sphere coordination compounds, including things like transplatin and cisplatin, you know, the compound that's much used in cancer therapy now. And here's a bit of philosophy from him. Scientific discovery is not yet predictable. If you have an exciting road to follow, don't be put off by those who say there's nothing at the end of it. They do not know. Persevere and enjoy the excitement of exploring the unknown. So when I was at the corporate lab, this is a much older picture, but I knew the young Howard Colquhoun, who had just started his research career there from Cambridge University, and the other person that comes into the equation here is a fine crystallographer, David Williams at Imperial College. And the reason for that is we eventually had crystals literally coming out of our ears. This was his research student at the time, who's now at St Andrews. And what we were studying was what became known as second sphere coordination. And so here are some examples. Here is a platinum complex shown here, which can be wrapped around by dibenzo 30 crown 10. It just wraps around like this. Your hydrogen bonding up here and donor acceptor interactions across here between pi electron rich and pi electron deficient units. It did not take a lot of as it were, thinking out of the box within the ICI context to say, well, if we could complex this one with a transition metal, why not try diquat, which is very, very similar, and lo and behold, we got a strong complex in solution and also have its crystal structure here. From there was the question of could we complex the other weed killer, paraquat, which is often called by others methyl-viologen. And we over-designed, but eventually it was a simple solution. It was a constitutional isomer of DB 30 crown 10, just move the loops from being ortho-related to being para-related. And Cram had made this compound and published it in JACS in 1978 for quite different reasons. So we just remade it, and lo and behold, it was a wonderful home for paraquat. And here is the crystal structure. And any time I look at this crystal structure, I know this is where we got the very strong message. You have a sort of rod-like molecule supramolecularly piercing through a ring. Didn't take much imagination to say we could put big stoppers after some extension on the end and we would be in the retaxane world. Or we could incorporate this, as we did, into a cyclophane where we have paraquat units on the east and west, joined up by paraphenylene units, and this became known as our little blue box. And so this slide just shows you that in donor acceptor terms, we could put blue inside red, i.e. pi electron deficient species inside pi electron rich ones, and then we could also put 1,4-dimethoxybenzene as an example of a pi electron rich system inside the blue box, which is pi electron deficient. And so here are the chemical building blocks that we used out of our experience at ICI, the weed killer, and also we moved over to using this 1,5-dimethoxy or dioxynaphthalene unit in much of our early work. All right, so I'm going to define some icons now. So when molecular recognition is switched on, I will show a lock with a key in it. When it's off, I will show the key out of the lock. And we will also have templation, which is happening, of course, between red and blue. Later on, I'll introduce radical templation, where I'll use purple. So this is where we have free electrons. We have radicals, obviously. Sometimes we'll use heat, sometimes we'll use electricity, redox control. Sometimes we'll see ratios of mechanically interlocked molecules that are not one-to-one, and sometimes we'll be able to address them with chemicals, i.e. acid or base. And so here's some movies that just show what I've been talking about. Here's paraquat finding its way into this crown ether, and you can see we're down on the sort of cubic nanometer scale. So we can put red into blue. In 1988, this was the dimethoxybenzene going into the little blue box. But we couldn't make the blue box very efficiently until we realized that it would be useful to template it. So here you see a template, and once this bond is formed and the box is made, we can use liquid-liquid extraction to withdraw the template and have the pure box. So that's establishing the molecular recognition. Let's see how we used them in the formation of catenanes and retaxanes. Well, this was the sort of big breakthrough experiment that was carried out in 1989 and published in Angewandte Chemie. And so we took a 3 molar equivalent of this crown ether and added these two components. And they don't talk to each other at all. There's no interaction, no supramolecular chemistry, until a carbon-nitrogen bond is formed here. And then this is just like paraquat, it's a bipyridinium species. No surprise, it wants to make its way inside here. And these vertical lines indicate that CHO, donor acceptor, and CH pi interactions are switched on. And then you change the counter ion, and then suddenly you have the last bond being made here, and you have a all organic 2-catenane and 70% yield. This was, in that particular year, just out of this world in terms of surprise. And here is the crystal structure. So that up from what I would call the northeast down to the southwest, we have acceptor, donor, and they're at 3.5 angstroms from each other, the same distance as we got in DNA. And then this particular hydrogen here is pointing into this pi system. So this is a CH pi interaction, similar to what you see in proteins. They're rich in amino acids. And so we're using the same weak interactions as the natural world uses. So here's a movie just showing the catenane formation. So it is sucked on by this bipyridinium residue, and then the final one is made. And not only do we switch on all the interactions, but we've now made a mechanically interlocked molecule. And so what does it do? Dynamic NMR spectroscopy shows that that ring will rock with respect to the red one, with respect to the blue one, 2 million times a second. A slower process that you can see at higher temperatures, 2,000 times a second, is what I call pirouetting. And then the slowest process of all is this one, which is 30 times a second. And I know there's people in the audience who've been interested in our molecular electronics. This was the particular process that we used in collaboration with Jim Heath when I went to UCLA to bring about switches that were used in so-called crossbar systems. I'm not going to have time to talk about that, so I just mentioned this is where it had its origins. So the next question was, could we do the same with a retaxane? And so we took this dumbbell where you can see 2 hydroquinone rings, and again, they didn't talk to each other. Under these conditions, we have the same collection of weak interactions, and at the end of the day, we get the 2-rotaxane. Of course, this is not so highly pre-organized in the language of CRAM. It's not a cycle, and so you don't expect the yield to be so high, and indeed, it came out at 32%. These yields have all, of course, been increased a lot since these early days. And so here's a movie showing you the retaxane being formed. in the same way as we saw the catenane. And once this carbon-nitrogen bond is formed, we have trapped this dumbbell on that ring. And so now we're set up, if I redraw that molecule like this in a linear way, it's a bit unreal, but it's the easiest way to show you. This ring can jump back and forth between two sites in a degenerate way about 2,000 times a second in hexadeuteroacetone. So again, this was done by dynamic NMR spectroscopy. Here is the movie that is just recalling what you saw on that previous one. And then the next thing we did was to say, well, let's desymmetrize the dumbbell component. Let's replace a hydroquinone ring with a biphenol and another one with a benzidine. And we rightly predicted that this was the more pi-electron rich, so the ring would spend more of its time there, 84% of its time at room temperature in, I think, acetonitrile, and 16% in on the biphenol. So here you see the movie that shows the ring is sitting here 4/5 of the time, and the other 1/5 of the time, roughly, it's sitting there. So now we have a non-degenerate molecular shuttle, but it was designed so that we could come along and protonate, for example, these nitrogens, in which case we would move this ring from the 84-16 ratio to 100% on the red unit, thanks to Coulombic repulsions between the positive charge here and the positive charge on the ring. And so if we wanted to reverse this, we would then add base, and it would go back to the 84-16 ratio. So here's the molecular switch. You see here that we published in Nature in 1994, where you have Coulombic repulsion then, and then when you remove it with base, it goes back and spends most of its time on the green unit. Okay, so where have we got to? We've got a shuttle and we've got a switch, but we've not made a machine. If you switch a switch on and you switch it off, you haven't done any work. And so just to introduce a machine, here in the macroscopic world, and this is thanks to a Dutch artist, these are sands in the Netherlands, and you see these wooden statues almost, but they're actually on the move with these sails, and it's obviously a windy day, moving all of this across the level sands. And here we're in the macroscopic world where inertia, momentum, friction, and gravity are all dominant. In our own world, as we had with the actin and myosin, with our biological motors, here you see another of these biological motors that is carrying a cargo in our bodies from one cell to the other. We're on the micro level, and now we're looking at thermal fluctuations. We're not in the, we've got constant moving Brownian motion, and these viscous forces have to have been dampened by the environment they're in. Physicist Dina Stumin has coined the phrase that they are swimming in molasses and walking in a hurricane. And so the difference here is the following. If we have a mechanical approach to moving something from here to there, then it's like a bicycle going over a mountain and over another mountain, and you get from here to there. Of course, you'll choose the lowest point, the so-called col on the mountain, to save yourself going over something that's too high. On the other hand, in the biological world and in our world of artificial molecular machines, think of this as a collection of molecules, maybe 25 of them. And so what we're doing now is juggling about with energy levels. We're using the energy profile here to raise this energy well up and tip the molecules into this energy well, which we've lowered here. And then in order to get to the next one, we raise this transition state here, we lower this one, and eventually we get over there. So it's all about juggling with energy wells and transition states. And so the first thing we did was to demonstrate the so-called flashing energy ratchet, where we have this pseudo dumbbell. It has a green neutral end and a blue positive end, a pyridinium 3,5-dimethyl pyridinium unit. And we surmise that the famous blue box will come on from the left here and go off by the right. So we're getting ready to make a machine, but before we do that, we need unidirectional motion. And so if we consider what happens when we mix these two, molecular recognition brings the ring on over the green end because there's no electrostatic repulsion. And then if we carry out a reduction, and this switches off molecular recognition altogether, then we also reduce the electrostatic forces, and it is ready to leave by the right-hand side. There's also, we believe, a shape change takes place with the ring that makes it less liable to come over the neutral end. And so if you look at this profile, what is happening is the rings are coming over the green end, and that gets us there. And then if we switch off molecular recognition by reduction, we raise the energy and we lower the transition state to come off the right-hand side. So that gives us a so-called flashing energy ratchet, which you see here repeated with this movie. And wherein it goes purple, this is when the recognition is switched off, when they become radical cations. And if it's oxidized, as you see it going on there, you have the molecular recognition, and you can control this just by an electrochemical cell. So now I want to just quickly introduce you, because I make a big issue of the fact that I give my postdocs and graduate students a huge amount of freedom. And here's an illustration of one of these stories. Here's Ali Trabolsi. He's from the Lebanon. He got his first degrees in the Lebanese University in Beirut. He then moved to the University of Strasbourg, and there he took his PhD in physical chemistry. So we go fast forward. He's now a professor at New York University, Abu Dhabi, in the United Arab Emirates. And so what did he do? So he actually did something that has been described by other people in my research group as being intellectually disruptive. After a life of 25 years, the little blue box, he asked himself, if I take paraquat, now he calls it methyl-viologen, and if I carry out a reduction, what will happen? And you know, he just built his own little glove box. It wasn't that we had the equipment, so he was very, very inventive. And lo and behold, he showed that a one-to-one complex is formed. And it's a strong complex that adds up to about 6.5 kilocalories per mole in acetonitrile. And of course, it's driven by enthalpy against a big entropy loss. He teamed up with a graduate student, Albert Fahrenbach, to get the X-ray crystal structure, where you see the radical cation here nestling through the reduced cyclophane to a bis radical dication, so it's a tris radical complex. And what's more, in the crystal, you have this infinite stack where all the electrons can move back and forth. And so I give a lot of credit to Ali Trabolsi, because that was a case of, he wasn't a synthetic chemist, he was prepared to do something in synthesis, was a game changer in my group. And the fact that it is a game changer is illustrated by the fact that all these men, and there's one woman here, followed in his footsteps. And so, just recalling what he did, he got this complex that is worthy of 6.4 kilocalories per mole of binding. And so you could come up with this thought experiment, turn the pseudo-dumbbell that we had before through 180 degrees and have the charged end here, and you can easily see that you can talk about a reduction to bringing the ring on under tris radical tricationic conditions, and then a relaxation to an oxidation of this whole system and force it over the right-hand side like this. And so this led to the design of something that became known as a molecular pump, where we have the blue box, we have a free 6-dimethylpyridine. I'll give you the chemical constitution in a minute. A bismethylene group, and then a bipyridinium residue, another bismethylene, and then this aromatic benzenoid ring with the isopropyl group. And this is often referred to as a speed bump, and a long collecting chain here. And so the fact that now we would not be letting the ring go back into solution as we would with the flashing energy ratchet, where no work is being done either. We would be collecting these rings on this chain, and as such, energy would be on the increase. And so you can see this little profile here showing how this could be done. And if we just go back to the beginning, under reduction conditions, you bring the ring on, and then with a bit of thermal energy after oxidation, you force it over there. When it reduces again, this ring wants to come back, but the speed bump stops it, and the second one comes on and joins it. Okay, so here's another movie just showing this routine. I'll let it go start again. Okay, so under reduction, the ring is coming on, molecular recognition, oxidation, thermal energy, forces it over the speed bump onto the ring. The second one's coming in, it stops the first one coming back, and the second one ultimately joins the first one. And so going through it, it's a question of reduction, followed by oxidation, followed by thermal energy, followed by further reduction, oxidation and thermal energy to get 2 on. So we can isolate a 2-rotaxane and a 3-rotaxane. All right, so that's the story. We're doing chemistry away from equilibrium, and here is the experimental evidence, one piece of it. Before I go there, here's the chemical constitution, the 3,5-dimethylpyridine, bridging bismethylene, the pyridinium residue, bridging bismethylene, the phenylene group with an isopropyl on here, and then this long connecting chain, the last step of the synthesis being a Sharpless-related click reaction. And so the dumbbell and the ring are subjected to treatment with zinc dust to do the reduction, and then with nitrosyl hexafluorophosphate, all in about 10 minutes. And this gets us to a stage where we have a spectrum of this kind, where the ring is sitting here, waiting on thermal energy to force it over. And you can already see these high field signals appearing, but if we have to wait at 42 degrees, we have to wait for an hour and a half for the ring to make its way over. And it turns out that we can repeat this, the same time schedule, an hour and a half to get the second ring on. And so this movie then I think illustrates what I'm talking about: reduction, oxidation, thermal energy to push the ring over onto the collecting chain, and then reduction, it wants to come back, stopped, comes on here, oxidation, everything goes back to 4+, 2+, and now coulombic repulsion forces the ring over with some heat onto the collecting chain to join the first ring. So it's a question of pumping one ring followed by 2 rings. We're doing chemistry away from equilibrium to get the 2-rotaxane and the 3-rotaxane. And to be honest with the outcome, the 90% yield is the production of the 2-rotaxane here after this redox process and the thermal energy. The most important number here is the free energy of activation for the crossing over of the speed bump, because this number turns out to be within experimental accuracy, the same as the second one. In other words, the passage of the second ring over the speed bump to join the first one is in no way influenced by the presence of the first ring. All right, so here's more of a thought experiment, because we didn't go on and do more than 2 rings on this one. Here is the way the profile changes as you do the reduction, and then the oxidation, and send a ring over. And I'm going to do this another 2 times. And what I want you to notice is I'm raising the energy of this level here, which is my argument for we've actually now got something that we can call a molecular machine or motor, because each cycle traps one ring in a high energy state. Some of the energy input is trapped, some will go to heat, of course, and finally one can say work is done. And this leads to what are called entropically dominated and even enthalpically dominated polyrotaxanes. Now, how could we improve upon this? Remember, we were having to use a temperature of 42 degrees. If we were to make some subtle changes, and here the methyl groups have been moved from 3,5 to 2,6, and one of the methylenes has been taken out of here, and this means that the coulombic repulsion between here and a ring on here is going to be increased. And so this chemistry was done, and you can see the same time scale was expressed at 298 Kelvin, but if we extrapolate up to 42 or 40, the whole process takes place within minutes. So this is where we are today, effectively, is using polymers to feed rings on to these long polymer chains. This could be polystyrene, it could be polyethylene glycol, whatever. And what's more, we're looking at doing it electrochemically. And so the situation that you see here is a long middle part that has 36 methylenes and a couple of ammonium sites. So it's not a very welcoming situation for putting rings on. Nonetheless, and this is work by postdoctor Dr. Christian Pizzato from originally Padova in Italy, beautiful NMR spectrum for his dual pump, that's for this compound here. And then he uses a home-built electrochemical cell to do some coulometry, and so at minus 700 millivolts he can bring the rings on over like this, and then wait a little bit and then do an oxidation and get the rings onto the collecting mid portion here, 2 of them at once. And you can repeat that whole process and generate a 5-ritaxane on top of his 3-ritaxane. And this slide just summarizes what he managed to do. Beautifully characterized the 3 and the 5-ritaxane reported in Angewandte Chemie. So our postdoc at the moment is now working on making polycationic ionic polyritaxanes based on a long polyether chain here, average molecular weight, couple of thousand, repeating unit average 50. And what Yunyan, and I'll introduce you to him in a minute, has been doing is to bring these on, first of all, chemically in what he calls a one-pot synthesis. And what this means is he doesn't isolate in between. He just uses cobaltocene as a reducing agent and nitrosyl hexafluorophosphate as an oxidizing agent, a bit of a rise in temperature, and he gets 2 rings on, he gets a 3-ritaxane. And then he just repeats it, he gets 5 rings on, and then 7 rings. And you can tell this from the integrations on the NMR spectrum. He goes on 9, 11, 13. Here you see him doing it more carefully, where he isolates everything in between. So he isolates this 3-ritaxane and then takes that and eventually takes it onto a 5-ritaxane, but at the same time he's also measuring the in the dosage spectrum the diffusion coefficient. And what you find with this diffusion coefficient is the number keeps going down in size as we go to 4 rings to 6 rings. So this is now 7-ritaxane, and this number is getting lower. And if you look at these 3, 5, and 7, you see that the situation is shown by the NMR spectra, and what is more, the situation involving the diffusion coefficient allows him to say that we're getting a more rigid molecule that has an average ratio of 15 here, up to 18, up to 19. And he's also repeated this work electrochemically using Christian's homemade apparatus, and got up as far as a 7-ritaxane at the moment, and he's every intention of taking it up as far as he can, which we think is round about a 13-ritaxane. And so the conclusions from all of this are the following, that rings can be pumped onto a PEG chain in pairs. The pumping relies on redox and thermal control, and the rings can be added chemically in one pot in pairs. That's just not isolating, just going round and round with the redox and heat. Or you can isolate and do it sequentially in pairs. and they can also be pumped on using electricity. So we have a big job in front of us to characterize everything here. We now are collaborating with somebody in Florida, a group there, in getting very good mass spec results, and they're coming through, but we need to look at cyclic voltammetry, light scattering, viscosity, imaging, and many, many other things before it's ready to be put out for publication. And so what you see here is a movie that just encapsulates what I've been talking about, namely the pumping of rings onto a polymer to give us a situation where these rings are not going to be very happy because they're all carrying 4 positive charges ultimately. Okay, and so I think I'm in for a little bit of a rest now. I'm going to have a recall of what I've been telling you with a little bit of music if we're lucky, and I hope you enjoy this recall of 35 years and 4 minutes.
Ni le bien qu'on m'a fait, ni le mal, tout ça m'est bien égal. Non, rien de rien. Non, je ne regrette rien. C'est payé. Mes chagrins, mes plaisirs, je n'ai plus besoin de balayer les amours avec leur trémolo, balayer pour toujours. Je repars à zéro. Non, rien de rien. Non, je ne regrette rien, ni le bien qu'on m'a fait, ni le mal, tout ça m'est bien égal. Non, rien de rien. Non, je ne regrette rien, car ma vie, car mes joies, aujourd'hui, ça commence avec toi. Non, rien de rien. Non, je ne regrette rien, ni le bien qu'on m'a fait, ni le mal, tout ça m'est bien égal. Non, rien de rien. Non, je ne regrette rien. C'est payé, balayé, oublié. Je me fous du passé avec mes souvenirs. J'ai allumé le feu, mes chagrins, mes plaisirs. Je n'ai plus besoin de balayer les amours avec leur trémolo, balayer pour toujours. Je repars à zéro. Non, rien de rien. Non, regrette rien, ni le bien qu'on m'a fait, ni le mal, tout ça m'est bien égal. Non, rien de rien, non, je ne regrette rien, car ma vie, car mes joies, aujourd'hui, ça commence avec toi.
Okay, so that's the story in terms of je ne regrette rien. I have nothing to regret. And so the main players were Scotsman Paul McGonigal, who teamed up with Chinese postdoc graduate student Chu Young Chen, and Chu Young is now at Scottishborn University as an assistant professor. Christian Pizzato, as I said, who came from Padua and is now at EPFL in Switzerland with a prestigious fellowship, getting more or less independence. And at the moment in the group we have Yunyan Chi. Okay, so just a brief survey. I could go back to 1970, but I go just back to 91, and you can see that it's taken 35 years or something to get from here to there. And there have been many, many players, both in the early days and the later days in this mission. Fortuitously, on the 7th of November, that was halfway between hearing from Stockholm on the 5th of October and going to Stockholm to meet the King on the 10th of December. This book was published by Wiley, The Nature of the Mechanical Bond. It's 6 chapters. The introduction, I think, is a very readable one, even for the layperson. Gets a bit tougher after that. This is synthesis under kinetic control, under thermodynamic control. And then chemical topology. I share the views of Jean-Pierre Sauvage, who believes that chemical topology is going to be big in chemistry in the next couple of decades. And then stereochemistry, and I'm going to emphasize here that I think stereochemistry is undergoing a potential revolution as a result of the invention of the mechanical bond. And then finally, a chapter on switches and machines. As far as stereochemistry is concerned, well, before I go there, this brilliant young graduate student, who's now a professor at the University of Colorado, really did most of the illustration and the hard work to get to that 800-page tome, I think we would call it, a big book anyway. And if I show all of this, you can see that we either had to invent or use terms that had been recently invented, 36 of them, and we just run out of space. So this is a message that stereochemistry, which is no longer just the prerogative of the stereogenic bond, the chiral center, or whatever you want to call it, but is now, in Prelog language, the remit of axis of chirality, planes of chirality, and helical chirality. So there's a lot to be done there. There's a Chinese version of the book in the making, thanks to ex-graduate student Andrew Su at Tianjin University with a couple of his students. And here's one where I want to illustrate something I feel very passionate about. Chemistry is not an old science. Chemistry is potentially the youngest of the sciences, and the reason for this is that we have this ability to create, as Marcin Berthelot said in French in 1850, to create our own object. And this is exactly what we've done with the mechanical bond. And you can see that catenanes and retaxanes really only took off about 1990. Now let me mention that in 83, my co-laureate Jean-Pierre Sauvage had described the first synthesis in tetrahedron letters in French. Note the lack of any need to publish in a high-profile journal if you have a Nobel Prize piece of work. In 83, his first synthesis of a catenate. This is where he used copper as the template. And his work continued, and you'll see that catenanes dominated for some time. We came in on the all-organic system in '89. The rataxanes followed, and you can see it's just been explosive in terms of catenanes, rataxanes, and even mixed catenanes and rataxanes. Of course, it's followed by citations, and good ones and not so good ones, maybe. Where's it happening? In the United States, the UK, here, of course, in Europe, but more so maybe in Japan and China. And as the intensity of the green grows around the world, hopefully there'll be more and more people taking up the chemistry of the mechanical bond. Some of the leaders are, of course, my co-laureates, Schoenberg Savage and Ben Feringa, not round the mechanical bond, but rather around some very elegant torsions about carbon-carbon double bonds that are orchestrated by the presence of some chirality and also the use of light, usually. Brilliant work. And then we collaborated a lot with the Italian group of Vincenzo Bolzani and Alberto Credi at Bologna, my ex-student David Lee at Manchester, and I think if Paya is here, yeah, she spent some time with David. Dina Stumian, I mentioned, physicist from Maine, who has given us lots to think about in a physical context. Here we have famous Czech scientist, Josef Mikl, who's spending, I think, more and more of his time in Prague now at the Czech Academy of Sciences, but originally in Boulder. Steve Loeb in Canada, at Windsor. Edie Sevick, an American at the Australian National University in Canberra. Mexican Miguel Garcia Garabi at UCLA. Rafał Klein from Poland at the Weizmann Institute. Amar Flood, New Zealander at Indiana University, and Armenian Ivan Ebrahimian at Dartmouth College, and Nicholas Giasponi in Strasbourg. So you can see how diverse the players have been from all parts of the world, and I don't think that's any accident. Let's just look at timelines in terms of if it's this pale blue, well, nothing was really happening, and then the green is meant to indicate a period of fundamental work before the, as it were, mauve comes into place here, where the particular engine has found great application. So obviously steam had its time. The electric motor is still with us, as is the internal combustion engine, the diesel engine, the jet engine, the rocket, our biological motors. Well, they've been always with us. It's only in recent times that we've been able to probe their existence. And then, of course, the ultimate is the artificial molecular machines. And so I'm not claiming too much about applications yet. I see them on the horizon, but we're still very much in the development of the fundamental work. And I want to just go back to János Jedlik from Hungary, who gave you this electric motor, which is still, as I say, working to this day. I want to point out that between 1827 and 1882, it's quite a big gap before people are building fans and food mixers in 1885, a much more modern one in the right-hand corner, and here's a 1920 hairdryer. So it does take time for these pieces of technology to be developed. Here at a rather more we say, I'm not quite sure how to put this, a level of lightheartedness, I think. We'll say that. Here's a tweet that I received. Your research on molecular machines has strengthened the development of nanobots. Okay. Also, it will help in developing swarm intelligence in nanorobots to the extent that they control the number of bots. Okay, so already people are obviously thinking about how they can use them in their particular science or engineering worlds. Where are they being used in material science? Well, there are things called slide ring gels, which have been developed by Ito in Japan, and they've found their way into scratch healing polymers that they put in Japan on the back of their mobiles or cell phones. And so a conventional scratch with a polymer will leave a scratch. With these sliding rings, the scratch will fill up very quickly. There's an interesting publication in Science a couple of years ago from an ex-student, Ali Joshkin and Yanwok Choi in Korea, where they find that these slide ring polymers actually lengthen the time or performance of lithium-ion batteries by stopping the coalescence of silicon nanoparticles in the binder here. Okay, so a little bit of philosophy to end with. I've got 2 minutes still. All right? Okay. So, what I want to share with you is what I strongly believe, that we're a little bit off the beaten track in the way we see science and fund science these days. So let's go back to just after World War II when Vannevar Bush, he was the scientific advisor to President Franklin D. Roosevelt, and he said, "Scientific progress on a broad front results from the free play of free intellects working on subjects of their own choice in a manner dictated by their curiosity and exploration of the unknown." And this led to the formation in the United States of the National Science Foundation, and I think it went just through a period of several decades of sheer, as it were, output that was amazing. And it's no longer there today. We're in a situation where it's an order of magnitude less in its influence on the country, and the money has gone to projects rather than to people. Helmut Schwartz, retiring chairman of the, our president of the Humboldt Foundation, has in an article in Nature Reviews Chemistry only a couple of years ago, fundamental research gives young people the opportunity to head for new shores. In order to master the future together, the enthusiasm of young people is the most secure currency we have. And he goes on to say, the principles of trusting people, rather than trusting monitoring systems based on distrust has proved its worth, and the principle of funding people, rather than projects has withstood the test of time. He knows what he's talking about. Outside of science, here is author Eleanor Caton, a New Zealander. She got the Man Booker Prize for her book called The Luminaries, a big book, in 2014, and she went back to her alma mater in Wellington, and here is what she said in the acceptance of her doctorate. The purpose of a university is not to replicate, but to enlarge, not to simplify, but to understand, not to reflect or serve the world in which we live. A very, very way out statement, but to enrich it through the creation and exploration of an infinity of possible other worlds. And so, in my own time, as I say, there have been a lot of people, and these are some from the recent past. We've been well funded through times in the UK, the US, and now from King Abdul City of Science and Technology. I want to come back to what Andre said at the beginning. I think diversity pays off big time. Science is global, and science knows no boundaries. In a 50-year period, we've been associated with 6 universities: Sheffield, Birmingham, UCLA, Northwestern, Tianjin in China, and UNSW in Australia. I spent 3 years at a company, and we now have 2 startup companies. And over all of this, I've dipped my time and energy into 4 different countries. And as we said at the beginning, in 50 years, 50 different nationalities, among 500 graduate students and postdocs have gone through my lab. And I've never seen any source of really serious friction. It's been one of camaraderie and a sort of family spirit, and everybody enjoying the food and fare of the other nation's culture. And then I just want to finish with a bit of Scottish poetry. And this poet, Robert Burns, who epitomized the period of the so-called Scottish Enlightenment, when we had philosopher David Hume, we had economist Adam Smith, who wrote The Wealth of Nations. We had a man called Joseph Black, who was the chemist, if you like. There was James Watt, the engineer, and a few more. But Burns is actually quite unique. He has more statues to him across the planet Earth than any other human being. And so a little bit of a translation from the Scottish, which you wouldn't understand. Then let us pray that come it may, as come it will for all that sense and worth over all the earth shall have preeminence for all that. For all that and all that is coming yet for all that. That man to man the world over shall brothers be for all that. And that's a message to the Brexiteers in the neighbouring country, England, who seem to have completely lost their senses. Finally, tackling a big problem. This came up in my discussions today with the students and also with the TV crew. And here's a comment from Venka Ramakrishnan, a 2009 Nobel Prize winner from the molecular biology labs in Cambridge. I found that almost nobody was working on routine problems just because they would lead to publishable results. Rather, they were trying to ask the most interesting questions in their field and then developing ways to address them. In my own language, I say doing your own thing, and so this is a little so-called classroom article in Nature Nanotechnology where I'll just pick out a few phrases. To achieve something that is impactful in contemporary science and to be singled out as a scientist who leaves their mark on science and ultimately technologies, you need to become recognized widely as having done your own thing. Now, this doesn't happen by magic. It means that at some stage during your career, you have to make a decision, and that decision is a conscious one to summon up enough courage to tackle a big problem for which no one has provided a satisfactory scientific answer. Tackle a big problem. And so I leave you with that piece of advice, and thank you all for the most marvelous day that I've had here in Brno. Thank you. So within 60 minutes, taking off the little time you used to introduce me.
Thank you, Fraser, for this fascinating talk. And now it's time for discussion. So, Sina?
Usually.
All right. You played with any kind of these molecular structures to make these, let's say, rotexanes form. Have you ever thought about putting an anion inside your axis? So, for example, something like a cyclopentadienyl anion, and then make it to, let's say, form and, let's say, you know, just goes away, and it can attract, for example, these cationic ring into the axis. Have you tried such a thing?
Okay, so we are working now on trying to get what we would call zwitterionic even catenanes, you know, one carrying 4 negative charges, 1 4 positive charges, and then what you're talking about, put the negative charge in the ring, in the dumbbell, in the rod, and then put positively charged rings on. I don't know that we, other than for fundamental reasons, want to go there, because the properties seem to be coming from when the rings are not speaking all that much to each other or to the rod component. This is where these slide ring polymers come in as slide ring gels, which at least have materials properties. So we are going more in the direction of switching off the interactions rather than switching them on. Yeah.
Thank you very much.
Okay.
Okay, other questions? I would actually have one about the polyrotoxanes.
Yeah.
I wonder, is there, do you think, any length limitation on the thread which you can use?
No, I don't think so. I think we could go for very, very long polymers, and it will, of course, ultimately, if we put on tens, hundreds of rings, which I think we can do, probably reach a point where, given the fact that these rings are also positively charged, there'll be a lot of coulombic repulsion. And, well, that's where we're heading. We want to switch off the interactions between the dumbbell and the ring. There's an interaction there at the moment with the polyethylene glycol chain, so we want to use something that will only give sort of van der Waals interactions. And so I've had people quite recently, when I've lectured on the topic, say, from a theoretical stroke physical point of view, we think you're on track to come up with another form of battery. So it's a little bit beyond me at this stage, but that's, I think, where we could be heading in a collaborative sense. Yeah.
Thank you.
Yes.
Fascinating talk. I did my PhD with Ben, and
Yes.
We always wanted to somehow bring about the function of our motors in a way that they would work in a collective, collaborating fashion, just like
Yeah.
in a muscle you have
Yes,
all
yes.
these fibers working together.
Yeah.
So do you envision to somehow take your molecules and make them work in an ensemble to manifest on a more macroscopic level?
Yeah, well, we went down that road when we collaborated with Jim Heath in the area of molecular electronics, and we started off in crossbar devices, only 2 terminal devices with 5 to 7,000 molecules with the first wires. The last ones we were down to wires that were, as I recall, about 17 nanometers in their width, and so we reckoned we had down to 250 molecules. And so these were all potentially working in concert with each other, although I would always say we were at the mercy of Boltzmann distribution. There would always be 1 or 2 that wouldn't behave the way we'd want them. And so I would argue the other way, that there is a number that you want to have that deals with the physical reality of the Boltzmann distribution, and give you, if you're looking at a switch, that opportunity to have most of your molecules working together in combination. So that's where we visited it already. We've talked about this a lot in relation to making polyuretaxanes that we call daisy chains, and Jean-Pierre Savage has been also active in this sort of areas to put many of these together and get them to work in unison, so that if you could repeat them over and over again, each movement is magnified as you go along a very long polymer, and so you get a long amount of contraction and extension. Yeah. These are all very much challenges that are up for the future, I would say, for the young people here. Yeah, take it up. Yeah. You must have had a wonderful time in Groningen, did you? Yeah. Were you there when the prize was announced?
I left about 3 months after the prize was.
Oh. So you've seen the storm that occurs. Yeah, yes. Crazy.
Okay, are there any other questions?
Give me a rough time, come on. Yes.
Those rings on the fret,
Yeah.
You are raising the energy and they are
Yeah.
repulsed from each other. Is there a concern that they can just jump off through quantum tunneling, or is it just something you are not concerned about?
Well, I think there comes a point where they can jump off, and we're already talking about how, when we get to a certain number where some judgment's got to be made, we actually do a swapping of the pumps for big stoppers, so that we avoid them coming off under any sort of traditional chemical way. So that's what we're thinking of doing, and I think we see how to do it, because there's a benzylic center in the pump, as it is adjoined to the so-called speed bump, and we think that's where we can intervene and put in by a swapping process a big stopper that is a dumb stopper, but will give us polyuretaxanes that will hopefully retain their mechanical properties forever. Up through the middle. Oh, but we're not in the. We're still in the classical world. We're not in the quantum world. So, yeah, I don't think it's a concern. I hope I'm right here. I don't want to put my foot in it and say that it couldn't happen. What's more realistic is we can manufacture the stoppers, and we did this way back in the mid-1990s at UCLA on our retaxane, such that under certain solvent conditions and temperatures you can slip rings on, and this usually takes about a month, and we got one retaxane that took a month in order to get to a 99.9% yield, and this was all done in chloroform, and it was based on hydrogen bonding. If we isolated it and put it in dimethyl sulfoxide, then overnight the ring came off. And so this illustrates that in much of chemistry, it's not black and white, your world, it's a series of grays. And so the question was raised when we did this work, were we working with a retaxane or were we working with a pseudo-retaxane? And there was a lot of argument in the group. And I went back to the teachings I had from Eliel on this sort of subject, and I said, well, it's a matter of you just define your conditions. Under these conditions, you have a complex, you have a pseudo-retaxane. Under these conditions, other conditions, you have a retaxane. So.
Okay. Do we have time still for one last question?
Thank you very much for the talk. I have a question out of curiosity. When you put these rings on the road, is it possible to have rings with different characteristics, so making a sequence of different things?
Yeah. So that's one that I think is wide open from the point of view of trying to make artificial polymers that would be in the same league as nature's proteins, where you can actually define the sequence of monomer units as a result of feeding on obviously different rings. And so what Yunyan is working on at the moment, there's absolutely no reason why we shouldn't have a blue box with some kind of, and we have many with functional groups. With one functional group, we bring two on, then another functional group pair, and then another functional group pair. I mean, it's still a long way from dealing with 22 amino acids and whatever, but I think that is one of the things that could be done. I agree.
Thank you.
Okay. Thank you, Fraser.
Mm-hmm.
Thank you very much for coming to Brno. You don't know, but we have been active today from 9 o'clock, and Fraser had about 5-minute break maybe today. He was going from interview to interview. He will be on Czech TV, also in Hyde Park Civilization, so watch. It's going to be really nice.
That was a great interview. You have the most marvelous person in this man, Daniel. He's quite unique. The extent to which he had done his homework surpassed anything that I've experienced with any interviewer right across the planet. He was absolutely on top of it. And it was thought out in a very, very, I think, organized way, and more than organized, I think, in an intellectually stimulating way. And I was amazed, absolutely amazed. So I hope the net result is worth watching in Czech, and I hope to look at it in my own native English, as I'm still struggling to get my mind around foreign languages.
I'm sure it's going to be an original as well. So as you can see, Fraser made a huge impact on Czech science today, within just about 10 hours, I think. Yeah, he is doing a big impact on the science worldwide, and I wish you all the best, all the strength to continue doing great things in chemistry.
Thank you.
And by that, we have a small present for you to remember.
Oh my goodness, more presents. Oh, wow.
The Mendel's medal.
Thank you. Cool. Oh. You hold that. Yeah, yeah. So,
If there is one thing which I learned also from Stoddart, you can make the influence on the chemistry and on the science by tweeting. So tweet.
yeah, yeah. Tweet to your heart's content, yeah. It's the way to put Brno on the map today, yes? We'll have a tweet storm tonight.
Yeah.
Yeah.
So
No rain, just tweet.
do you think if everyone took a picture of us and tweeted it,
Yeah, yeah.
would it be the storm?
It would be incredibly strong, and you know, this might be a way by which science can come back and be really, really powerful. So go home tonight and think about if a clown like me, if a wee laddie like me with very, very little nous, to use a Scottish word, can learn how to tweet. Everybody in this room can do it. Yeah? Yeah? Okay. Thank you.
Okay.
Thank you.